Hello everyone. We're going to keep working through an example we started before actually. We had a recurrence that was a divide and conquer type recurrence, t of n over 3 plus cn. And we analyzed this sort of in a hard, time-consuming way. I'm going to show us a slightly better way. All of the first steps involving the substitution are not optional. There's no way around those steps. But sometimes you can get away with better tricks for the summation. So for this problem, we had a summation that looked like cn over 3 to the I. So I'm going to analyze that in a different way now. So we wanted to analyze the summation from I equals 0 to k minus 1 of cn over 3 to the I. Typically with geometric type summations, things raised to powers, the best way to attack them actually typically turns out to be by bounding. So let's bound this above. Bound above. To bound it above, we are going to take the original summation from I equals 0 to k minus 1 of cn over 3 to the I. Maybe first we pull out the cn. That seems like a reasonable first step. Then it is the sum from I equals 0 to k minus 1 of a third to the I. The same stuff we did before. Now, because it's a geometric type summation, we typically bound it with a infinite geometric series. So we go from I equals 0 to infinity. That's adding up many, many more terms than we had originally, and definitely makes it bigger. And now this has a convenient formula. So maybe we recall our formula, sum from I equals 0 to infinity of r to the I, was equal to 1 over 1 minus r, so long as r was less than 1. Is that true for what we have here? Well, let's check. Our r value is 1/3. Last time I checked, 1/3 is less than 1, so math seems to be okay. So I still have a cn out front, but then the summation I'm replacing with 1 over 1 minus r. So 1 over 1 minus a third. 1 minus a third is 2/3. So that's cn times 1 over 2/3, which is just 3/2 times cn. So we bounded it above and show that it is in big O of n. We need to bound it below. Bound below. To do that, we take the summation, the sum, from I equals 0 to k minus 1. Maybe we even start with the cn out front and write it as a third to the I to save ourselves some pain. All of those simplifications work regardless of how we're bounding it. This is a bit of a cheat for bounding it. That entire summation, I could write it as 1 plus, let's not even do a greater than or equal to yet. I could write it as 1 plus a third plus a ninth plus all the way till we get to 1 over 3 to the k minus 1. That whole summation is definitely bigger than or equal to just the first term of the summation. In this case, that's 1. Hey, look, cn times 1, that's pretty obviously in big omega of n. And now we've shown the summation is in big O of n in the red part and big omega of n in the blue part. So the original summation from I equals 0 to k minus 1, k minus 1 of cn over 3 to the I is in theta of n. Just like we showed the last time we attacked this problem, but this is much easier. For almost any problem of this form, I strongly recommend doing it this way because it tends to make the math much simpler. But to each their own. So, exactly like we showed before, we can determine the complexity of that summation.